Good evening everyone, good evening. I welcome you all again to your Vedantu ENLITE channel. I hope you all are doing great, having a good time. So people, quickly, before starting the session, just let me know in the chats if I'm perfectly audible and visible to everyone. Hello Rajneet, hello Mukaddas, hello Akash, hello Aisha, hi Chena, good evening everyone. Just let me know quickly in the chats if I'm perfectly audible and visible to everyone, my dear people. Yes? Hello Pariti, welcome back to the session. Just give me some green signal from the chats, people. Perfect, just give me a second, we'll be starting, yeah? Just give me a second. Alright people, so in the tonight's session, what we are going to talk about exactly? Well, we shall be doing the most expected questions from the chapter chemical bonding, right? And in this particular session, I have come up with around some 30 to 35 questions from the chapter chemical bonding, which is absolutely going to help you out, right, in revising a lot of concepts, and these are going to be the real important questions from the chapter chemical bonding, right? So before starting this particular session, my dear people, let me quickly introduce myself. So the ones who do not know me, let me tell you, my name is Wassim and I'm your chemistry master teacher right here on this Vedantu ENLITE channel, right? Well, the ones who have not liked the video yet, please do like the video, share the video with your friends, do subscribe to the channel, and do not forget to hit the bell icon so that you get the notification of every single session which we take live on this Vedantu ENLITE channel, right? So do like the video, share the video with your friends, and do subscribe to the channel as well, okay? Perfect, guys. So let me quickly know in the chats, my dear people, if all of you are super duper excited about this particular session as well, yeah? Let me quickly know. Let me quickly know, my dear people. Hello Sonalika, hello Parithi, hello Umar. Welcome back. Hello Arvind. Hi Atiti, welcome everyone. Welcome back. Perfect, guys. So let's get going then. Let's get started with tonight's discussion with the first question, which is going to be on your screen in 3, 2, 1, and now. This is the first question from the chapter chemical bonding, which is on your screen, my dear people, yeah? Look at the question carefully. The question says, the ion that has sp3d2 hybridization. We need to see that ion wherein the central atom has got sp3d2 hybridization, right? So we shall be checking one by one, my dear people, right? We shall be checking it one by one. Perfect. Yeah. Now, if you look at the first option, my dear people, the first option says the ion is basically ICl2 negative, right? So let me call this I as the central atom over here. How many valence electrons iodine has? You guys know it's a group 17 element, right? Sorry. Yes, iodine is a group 17 element. It's the halogen. So it has got some 7 valence electrons. So there is a negative charge over here. I'm going to add this negative charge, right? So 7 plus 1 comes out to be 8. How many terminal atoms are attached? There are 2 terminal atoms attached, right? The number of terminal atoms always gives you the number of sigma bonds. So this iodine is forming 2 sigma bonds, right? Now people, out of 8 valence electrons, iodine is using 2 of its valence electrons to form 2 sigma bonds. So there will be 6 electrons left as such on iodine in the form of 3 lone pairs, right? So there are 3 lone pairs as well. Perfect. 2 sigma bonds, 3 lone pairs, right? 2 sigma bonds, 3 lone pairs. Is that right, people? So let's calculate the steric number. Steric number comes out to be 3 plus 2, 5. That means it's going to be sp3d hybridized. So you got to know the first species among all is sp3d hybridized. But I'm supposed to check that one which has got sp3d2 hybridization, right? So first one cannot be the answer. Look at the second one, my dear people. The second one is going to show the same hybridization because this is this element Br. It is the group 17 element. There is a negative charge, 2 sigma bonds. So this again sp3d. This is sp3d. Similarly, you have got ICl4 negative. Let's check this out too. If I talk about ICl4 negative, my dear people, see, iodine, it has got some 7 plus 1, 8 valence electrons. It's forming 4 sigma bonds. There'll be 2 lone pairs as such on iodine, right? There'll be 2 lone pairs as such on iodine. So 4 plus 2 is 6. Steric number is coming out to be 6. And if the steric number is 6, the hybridization is simply going to be sp3d2, right? As simple as that. Out of 8 valence electrons, iodine is using 4 of its valence electrons to form 4 sigma bonds. So 4 electrons will be left as such on iodine in the form of 2 lone pairs. That's why its hybridization comes out to be sp3d2. So it's going to be option C, which is the correct answer of this particular question, my dear people, right? This one you can check on your own after this, right? 6 sigma bonds and 1 lone pair. So it's going to be sp3d3. Let me move on to one more question. Among the following molecules or ions, which one is diatomic and has the shortest bond length? Which one is diatomic and has the, which one is diamagnetic and has the shortest bond length, right? Well, people, this question is based on what? This question is based on the bond order, right? Let me first of all tell you something important. Whenever you will see a 14 electron species like N2, right? Whenever you see 14 electron species, its bond order is always going to be 3. Whenever you see a 15 electron species, its bond order will be having 2.5. 16 electron species will have the bond order of 2. 17 electron species will have the bond order of 2.5. 18 electron species will have the bond order of 2, right? Similarly, 13 electron species, right? It will be having the bond order of 2.5. 12 electron species will have the bond order of 2. 11 electron species will have the bond order of 1.5. And 10 electron species will have the bond order of 1, right? Now, people, this is C2 di negative over here, right? So how many electrons are there in C2 di negative? One carbon has got 6 electrons. So 2 carbon atoms will have 12 electrons. And there is di negative as well. So it is a 14 electron species, right? So C2 di negative comes under the category of 14 electron species. O2, it is a 16 electron species. O2 di negative, it is the 18 electron species. N2 di negative, it's again the 16 electron species. N2 di negative. First of all, let's have a look which among the 4 has got the maximum bond order. You can see it is basically going to be C2 di negative, which has got the maximum bond order. If it has got the maximum bond order, you know bond order is inversely proportional to bond length, my dear people. If it has the maximum bond order, it will be having the minimum bond length, right? So the minimum bond length among all will be for C2 di negative, right? And similarly, if you look at this, its molecular orbital configuration, it won't be having any unpaired electron in its molecular orbital, which makes this C2 di negative, the 14 electron species, as the diamagnetic in nature. So correct answer of this question is absolutely going to be option A. I'm sure it is clear to everyone, right? Perfect, guys. So let me quickly move on to one more question. This is one more question on your screen, and you guys are going to tell me the answer of this particular question in the chats. The correct statements among all. We are supposed to see which of the statements are correct among the 3 statements given. Valence bond theory cannot explain the color exhibited by the transition metal complexes. This is absolutely correct statement, right? Valence bond theory was not able to explain the color of the transition complexes, right? The first statement is absolutely correct. Valence bond theory can predict quantitatively the magnetic properties of transition metal complexes. It was not the valence bond theory by means of which we could talk about the magnetic behavior of different complexes. It was not the valence bond theory, so option 2 is not correct, right? It was basically molecular orbital theory by means of which we can check which species is diamagnetic, which species is paramagnetic, right? And if you talk about the complexes in your coordination chemistry, you would have studied the crystal field theory as well. That gives us the idea about the magnetic properties as well. Anyways, have a look. Valence bond theory cannot distinguish ligands as weak and strong field ones. Absolutely. Valence bond theory gives no idea about the strength of the ligands, right? So first and the third statement are correct. Second one is incorrect, my dear people, right? First and third one are correct. I'm moving on to one more question. Which of the following molecule has got the net dipole moment of 0? What do you think about this one? Which of the following molecule has got the net dipole moment as 0? Well, people, if you talk about this chlorine, it's electron withdrawing. If it is electron withdrawing, it will carry delta negative, and over here it will carry delta positive. Similarly, this chlorine, delta negative, and over here delta positive. So basically over here you got 2 dipoles, right? This is the first dipole which you got. This is the second dipole you got, right? And the direction of dipole moment in chemistry we take from positive to negative. So this is the direction of dipole moment, and this is the direction of dipole moment. Since both are equal and in opposite directions, they cancel out each other's effect. So net dipole moment of this one is going to be 0. In the similar way, In the similar way, just a second, this is Cn over here, right? This is Cn. In the similar way, the net dipole moment of this one is also going to be 0, right? But people, the net dipole moment of third and fourth one, it is going to be non-zero, right? Because their dipole moments, they are not exactly opposite, they are not exactly in opposite direction, which is why their dipole moments do not exactly cancel each other, right? Which makes this molecule to be polar one, whose net dipole moment is going to be non-zero, and this molecule, its net dipole moment is again going to be non-zero only, right? So do remember, it's going to be third and fourth one due to the spatial arrangement of these OH groups and SH groups, right? Their net dipole moment comes out to be non-zero. So it's basically option 3 and 4, wherein the net dipole moment is non-zero. Okay, look at the next one, my dear people. Then sum of the number of lone pair of electrons on each central atom in the following species. So we are given with certain species. The first one is TeBr6 dinegative, right? Have a look, my dear people. Let's call this as a central atom. It belongs to oxygen family. It has got some 6 valence electrons, right? But there is a dinegative charge, so add it up. So make it 6 plus 2, 8. How many terminal atoms are there? 6 terminal atoms. The number of terminal atoms always are equal to the number of sigma bonds. So 6 sigma bonds. Out of 8 valence electrons, 6 of the valence electrons are used to form 6 sigma bonds. So there'll be 2 electrons left as such on tellurium, right? That means there is 1 lone pair on Te. Perfect. So 1 lone pair. Look at the next species which is given to me. It is Br(F2) positive, right? Br(F2) positive. So how many valence electrons are there with this bromine? 7. It's a group 17 element, right? 7 valence electrons. But there is a positive charge as well, so subtract it. So 7 minus 1 comes out to be 6. How many terminal atoms are attached? 2. So there are 2 sigma bonds. How many lone pairs will be there? Out of 6 valence electrons, this bromine has used 2 of its valence electrons to form 2 sigma bonds. So 4 electrons will be left as such on bromine in the form of 2 lone pairs. So there are 2 lone pairs on bromine right here. Similarly, if you talk about XeF3 negative, right? Xenon, it is basically a noble gas. It has got 8 valence electrons. So negative charge, so add this up, so it makes it 9. How many sigma bonds? Since there are 3 terminal atoms, so 3 sigma bonds. How many lone pairs? Out of 9, it is using 3. So there'll be 6 electrons left as such on xenon in the form of 3 lone pairs, right? So there are 3 lone pairs. What do I need to calculate basically? I need to add the number of lone pairs on the central atoms. So 1 plus 2 plus 3. 3 plus 2, 5, 1, 6. So 6 is going to be the correct answer of this particular equation. So it's going to be option D, which is going to be the correct one among all. Right, people? If it is clear to you, let me know in the chats. Let me know in the chats if it is clear to everyone. Yeah? Exactly, Akash. Exactly, Manisha. You're right. Exactly, Janvi. Exactly, Bhavya. Good job done. Now let's have a look on this particular equation. In which of the following pairs the 2 species are not isostructural? The 2 species are not isostructural. Well, if I look at all the options, my dear people, if you look at this particular one, have a look. It is PF5, right? It is PF5. And there you have got one more, that is BRF5. Perfect. Let me tell you, this phosphorus, it's making 5 sigma bonds. And since phosphorus, it has got some 5 valence electrons, and it has exhausted all its valence electrons, all its 5 valence electrons to form 5 sigma bonds. So there'll be no lone pair on phosphorus. So steric number comes out to be sigma plus lone pair, that's 5. So its hybridization is going to be sp3d, right? Its hybridization is going to be sp3d. Now look at this one, my dear people, right? There'll be 5 sigma bonds which this bromine is forming, and there'll be a lone pair on bromine as well. There is 1 lone pair because bromine has got some 7 valence electrons, out of which it is using 5. So 2 electrons are left as such on bromine in the form of lone pair. So 5 plus 1, the steric number comes out to be 6. If the steric number comes out to be 6, the hybridization is going to be sp3d2. So people, these are basically the 2 species wherein the hybridization is different. And whenever you'll be seeing 2 species which will be having different hybridization, they're absolutely not going to be the isostructural species, right? There is one property of the isostructural species. Isostructural species, they have got same hybridization, But over here, if you look at these two species, they do not have the same hybridization, so they are not going to be isostructural among all. Well, if you look at all the other options, my dear people, you can check it out. In all the other options, the hybridization is going to be same, right? As simple as that. Perfect. Let me quickly move on to one more question. This question is based on the Fajan's rules, right? You need to see the maximum covalent character among all, yeah? Well, people, in order to talk about the covalent character in an ionic bond, we use Fajan's rules, right? Have a look. I'm sure you all must be knowing covalent character. First of all, have a look, guys. Have a look. This is Fe di positive right here. This is Cl negative. Sn di positive, Cl negative. Al tri positive, Cl negative. Mg di positive, Cl negative. N ion everywhere is same. N ion everywhere is same, right? So you will be deciding on the base of cation. You will be deciding on the base of cation. And moreover, the charge on cation is varying. Have a look. Covalent character in an ionic bond, it depends on the polarizing power of the cation, right? And polarizing power of the cation is directly proportional to charge on cation and inversely proportional to the size of cation, right? More the charge on the cation, more will be the polarizing power of the cation, more will be the covalent character in an ionic bond. Now you need to see exactly wherein the cation has got the maximum charge. The cation has got the maximum charge here, so it's going to be maximum covalent among all the species. As simple as that, right, people? Yes? Absolutely, guys. It's going to be option C, which is the correct answer of this particular question. Look at the next one. Let me know its answer first. I'm looking at your chats only. Give it a try and quickly let me know the answer of this particular question. The hybridization of nitrogen atom in NO3 negative. So first of all, you have got NO3 negative, right? Since if you talk about nitrogen, which is a central atom, how many valence electrons nitrogen has? 5. There is a negative charge, so add this negative charge, so 5 plus 1, 6, right? How many sigma bonds it's forming? It's forming 3 sigma bonds because there are 3 terminal atoms attached, right? Now people, oxygen being divalent, and there are 3 oxygen atoms, right? So nitrogen, it has got 6 valence electrons right now, so it would have used all its 6 valence electrons to form 6 bonds with oxygens, right? So there'll be no lone pair left on nitrogen as such, right? So steric number comes out to be 3, right? So hybridization is going to be sp2, as simple as that, right? Then you have got NO2 positive. You have got NO2 positive, my dear people, right? Valence electrons, 5. There is a positive charge, so subtract it. So 5 minus 1 comes out to be 4, right? How many sigma bonds? There are 2 sigma bonds, right? Oxygen being divalent. So all the 4 valence electrons of nitrogen are exhausted because oxygen is divalent, so there is no lone pair. So 2 plus 0 comes out to be 2. So hybridization is going to be sp. So sp2, then sp, sp2, then sp, then last one is automatically going to be sp3. So option B is the one which is correct among all. As simple as that. Well, you can solve the question if you remember their structures as well, right? You can do that. Let me move on to one more question, my dear people. IF7. If you talk about IF7, my dear people, very common molecule this is. Valence electrons of iodine, 7. How many sigma bonds? 7 sigma bonds. How many lone pairs on iodine? 0. Steric number, 7 plus 0 comes out to be 7. Hybridization, sp3d3. And for sp3d3 hybridization, you must be knowing the structure is going to be pentagonal bipyramidal, my dear people, right? Yes? Pentagonal bipyramidal. So it's option D, which is the correct answer of this particular question as well. Yeah? Perfecto. Let's move on to one more question, my dear people. This is one more question. Let's have a look. Identify the species having 1 pi bond and maximum number of canonical forms. Which of the following contains 1 pi bond and maximum canonical forms? It's going to be CO3 di-negative, which contains 1 pi bond, right? 1 pi bond and maximum canonical forms, right? One more canonical form of this one is going to be like this. Shift it this way, shift it this way. So it's going to be C, oxygen carrying negative, this oxygen carrying negative, and there's a double bond over here. It's one more canonical form will be like this. Shift this in this way, right? Then shift in this way. Perfect. It's one more canonical form. It's C, double bond O, this oxygen carrying negative, this oxygen carrying negative too. So CO3 di-negative, it is a structure which contains 1 pi bond and it has got maximum resonating structures, maximum canonical forms among all the species which are given to us. As simple as that. So option A is the one which is the correct answer of this particular question, my dear people. Moving on to one more. Which of the following is V-shaped? Well, let me tell you, V-shaped molecule is of the type AB2L2. Whenever you'll be having a molecule wherein there'll be 2 sigma bonds, there'll be 2 sigma bonds, and there will be 2 lone pairs on the central atom, right? 2 sigma bonds, 2 lone pairs on the central atom. We say that molecule is going to be V-shaped, right? Like water, bent. Now, if you look at S3 dinegative, right? Just to make you understand, I'm going to write S3 dinegative as SS2 dinegative. I can do that. Just to simplify it a bit, right? SS2 dinegative, which is basically S3 dinegative. See, sulfur, it belongs to oxygen family. How many valence electrons it has? 6. But there is a dinegative charge, so make it add 2. So make it 8. How many sigma bonds? 2 sigma bonds, right? Since sulfur being divalent, right? So people, out of 8 valence electrons, 4 valence electrons will be used, right? So there'll be 4 electrons left as such on sulfur in the form of 2 lone pairs. So there are 2 lone pairs, 2 sigma bonds, 2 lone pairs. Steric number comes out to be 4. Hybridization is going to be sp3, right? And if there are 2 sigma bonds, 2 lone pairs, absolutely it's going to be V-shaped, bend-shaped, right people? Option A is the one which is the correct answer of this particular question, right? Simple. Yes, Janvi, resonating structure means canonical structures, right? Which of the following has maximum number of lone pairs associated with xenon? Which of the following has got maximum number of lone pairs associated with xenon? People, have a look. Have a look. Have a look fast. What is the correct answer of this question? This is something which you should solve now. Absolutely, Janvi, it's option D, right? See, least sigma bonds in option D. Least sigma bonds in option D. Central atom everywhere is same, right? But least sigma bonds in option D. So maximum lone pairs in option D. You can check it out too. It'll be having 2 sigma and there'll be 3 lone pairs on xenon. There'll be 3 lone pairs on xenon, right? In this one, there will be only 1 lone pair. There'll be 2 lone pairs over here on this xenon, right? And there'll be only 1 lone pair on this xenon. You can check it out, right? Simple and basic. Which of the following order of energies of molecular orbitals of N2 is correct, right? How do you fill the electrons in the N2, right? In the 14 electron species. How do you fill it? Have a look. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2p x, pi 2p y, sigma 2p z. This is the correct order, my dear people. Option A is the correct order, right? This is something which you need to remember basically. This is something which you need to remember. Whenever you'll be having the species which contains electrons less or equal to 14. This is the order in which you are going to fill the electrons in the molecular orbitals. And any species which contains electrons more than 14, this is going to be the order which you guys are going to follow, right, to fill the electrons in the molecular orbitals. I would want you guys to remember them and do take screenshot of these 2 things as well, right? These are 2 important orders from which majority of the question comes in your from the chapter chemical bonding, like questions based on bond order, bond length, bond strength, paramagnetism, diamagnetism, right, and so on. Perfect. So do remember them. Anyways, moving on. Match list 1 with list 2. What is list 1 saying? SF4. SF4. People, 4 sigma bonds, 1 lone pair. 4 sigma bonds, 1 lone pair. So 4 plus 1, 5. 4 sigma bonds, 1 lone pair. 4 plus 1, 5. 5 means sp3d, right? I have 5. 5 sigma bonds, 1 lone pair on iodine. 5 plus 1, 6. sp3d2, right? Check the options, my dear people. Attach A with 3. Attach A with 3 and attach B with 1. Attach B with 1. So option D is the one which is correct among all. Yes, Akash, you're absolutely right. Absolutely. Well, you can check the rest as well, right? This is going to be sp hybridized and this is going to be sp3 hybridized only, right? Simple. NO2 positive, we have calculated its hybridization few minutes back only. All right, people, moving on to one more. The central atom in a molecule. We have got a central atom in a molecule which has got 2 lone pairs and forms 3 sigma bonds. So the type of the molecule is going to be AB3L2, right? AB3L2 type, my dear people. What is going to be the shape of it? If this is the central atom, this is the central atom, right? This is 1 lone pair present at the equatorial position, 1 more lone pair present at the equatorial position. This is one of the bond pairs present at the equatorial position, and on the axial position 1 more bond, on the axial position downwards 1 more bond. So what do we call this shape as? 3 sigma and 2 lone pairs. This is what we call as T-shaped molecule. You can check it out. It's a T-shaped molecule. Simple, basic, right? Right, my dear people, it's T-shaped, absolutely. Yeah, these 3 are present in the equatorial plane. Right, this B is present perpendicular to the equatorial plane upwards and this B is present perpendicular to the equatorial plane downwards. Let me show it to you like this. Right, people? Perfecto. Let's move on to the next question, my dear people. Among the following, the linear species is NO2, very common example, my dear people. It's a bent shaped. Cl2, again bent shaped, right? Again bent shaped, same structure as that of water. O3, again bent shaped. N3 negative is the one which is going to be D, which is going to be linear among all, right? Yes, this is something which you need not to solve. You need not to use the pen and paper, my dear people. NO2, this is something which everyone knows. It's bent. Cl2, it has got the same water-like structure. It is bent. O3, it's again bent. There is only N3 negative, which is linear among all, right? This is bent, 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 and linear at the end. Let me quickly move on to the next question. Which of the following possesses some dipole moment? See, SF6, my dear people, it does not possess any dipole moment. It's perfectly octahedral. All the dipole moments gets cancelled out, right? SO2, it's bent. It carries the dipole moment. H2S, it's again carrying dipole moment. SF4, seesaw shaped. It carries the dipole moment, right? This is the only structure which does not carry the dipole moment because its structure is something like this. This is F. There's one more F over here. This is F. And this is F, right? And all these 4 fluorine atoms, they are present on the same plane, and this fluorine atom is perpendicular upward, this fluorine atom is perpendicular downwards. So on the plane, all the dipole moments are getting cancelled out, and perpendicular to the plane, again all the dipole moments will get cancelled out. So net dipole moment of this molecule is 0. If you look at all the other species, they will be having some of the dipole moments, right? So perfectly and regular octahedron species always will be having the net dipole moment if its terminal atoms are same all the time, right? So answer of this particular question is going to be B, C, and D. Right, as you can see the structures, my dear people. See, all the dipole moments are getting cancelled out here, but it is bent, so net dipole moment will be there. Similarly, seesaw shaped, perfect, there will be net dipole moment. Again, there will be net dipole moment, as simple as that, right? Okay, the correct shape and I bond angle respectively in IO3 negative. It's I3 negative, sorry, right? See, you have got I3 negative, my dear people. Just to simplify it a bit, I can write it as I2 negative, right? This iodine, it has got some 7 valence electrons, negative charge, so 7 plus 1 is equal to 8. How many sigma bonds? There are 2 terminal atoms attached, so 2. So how many lone pairs will be there? Out of 8 valence electrons, 2 of the valence electron have been used, right? There are 6 electrons left as such on iodine in the form of 3 lone pairs, right? So 2 sigma, 3 lone pairs, it's going to be sp3d, right? What about its shape? Its shape is going to be linear. If this is one iodine, this is one lone pair, this is one more lone pair, this is one more lone pair, and this is iodine perpendicular upwards, this iodine perpendicular downwards, right? The shape is going to be linear, my dear people, right? And these are the 3 lone pairs which belong to the central iodine, which are present on the equatorial plane, right? This one and this one, they are present on the axial plane, right? So it's going to be linear, and at the same time, I bond angle is going to be 180 degree, right? I bond angle is going to be 180 degree. As simple as that. Perfect? Absolutely, guys. Let me move on to one more. The species having the pyramidal shape is. The species having the pyramidal shape is. So pyramidal shape will be shown by that species wherein you find 3 sigma bonds and 1 lone pair. Any species wherein you find 3 sigma bonds and 1 lone pair, it's absolutely going to be pyramidal, like NH3. NH3 is pyramidal, right? Now, as far as I can see the options, my dear people, it's going to be OSF2, which is going to be pyramidal. Why is that? See, this is sulfur, this, for example, oxygen, this is one of the fluorine, this is one of the fluorine, this is the rough structure of it, which I'm making. See, guys, sulfur being the central atom, right? It has got some 6 valence electrons because it belongs to the oxygen family. Right, so how many sigma bonds are there? There are 3 sigma bonds, right? 1, 2, 3, and 4. Out of 6 valence electrons, 4 of the electrons have been used by sulfur, so there'll be 2 electrons left as such on sulfur in the form of its lone pair, right? So 3 sigma 1 lone pair, right? 3 sigma 1 lone pair means pyramidal, right? Right, people? As simple as that. Well, you can check the rest of it. They are not going to be the pyramidal ones. Right? Okay, the dipole moment. See, guys, the order of dipole moment. Let me tell you, this CCl4 tetrahedral, CH4 tetrahedral, all the same terminal atoms, So they'll be having net dipole moment 0. And this one, it won't be having net dipole moment 0, right? This one won't be having the net dipole moment 0, right? Because all the atoms are not same. All the terminal atoms are not same. Perfect. So CCl4 and CH4, they'll be having net dipole moment 0. So they are having net dipole moment equal, that means 0. And CHCl3, definitely it will have some of the dipole moment, right? Its net dipole moment won't be 0. Simple. Let me move on, my dear people, to one more question. This is one more question based on what? What do we have to see in this particular question? We are going to arrange them on the basis of the dipole moments. Let's have a look exactly how to arrange them, my dear people. CH3, it is electron donating. If it is electron donating, it will get delta positive here. This will get delta negative. Similarly, this CH3 electron donating, delta positive, delta negative. So I got one dipole moment whose direction in this way, one more dipole moment whose direction in this way. So net dipole moment of this molecule is going to be 0, as simple as that, right? Similarly, look at this one. Delta positive, delta negative, delta positive, delta negative. This is one dipole moment, positive to negative. This is one more dipole moment, positive to negative. Now both these dipole moments, one pointing downwards, one pointing like this, right? They are having an obtuse angle in between, right? Okay, look at this one. Delta positive, delta negative. So net dipole moment is downwards, right? This is delta positive, delta negative. So net dipole moment is in this way, right? Is in this way. Perfect. Now people, the minimum dipole moment is for A, right? Maximum dipole moment is for 3, right? Because two dipole moments, they are having less angle in between them, right? The magnitude of net dipole moment will be maximum in 3, followed by 2, followed by 1. So 3, 2, 1 is the order of the dipole moments, right? 3 has maximum, followed by 2, followed by 1. Option B is the one which is correct. Yes? Perfecto. Let's move on to one more. This is the similar sort of question, and I'm sure you can solve this sort of question on your own and have a look exactly how you're going to do it. CH3, electron donating. So delta positive, this one delta negative. Dipole moment, downwards. It is electron withdrawing, NO2, delta negative, delta positive. Dipole moment in this way, right? So one dipole moment downwards, one dipole moment over here. The angle is obtuse, right? Similarly, delta positive, delta negative. Dipole moment downwards, perfect. Electron withdrawing, delta negative, delta positive. Dipole moment in this way, right? So dipole moment in this way. Similarly, this is delta positive, delta negative. So dipole moment downwards. Similarly, this delta negative, delta positive, dipole moment again downwards. So two dipole moments having 0 angle in between them. So net dipole moment will be maximum in the third case, followed by second, followed by first. Again, 3, 2, 1 is going to be the correct order of this particular equation, right? Simple, my dear people. Yes? Okay, number of lone pairs around phosphorus in PCl5. See guys, in PCl5 there'll be no lone pair on phosphorus. It's a regular geometry. This is P, this is Cl, this is Cl, this is Cl, and these three chlorines, they are present on the equatorial plane, and this is axial one, this is axial one. This is the structure wherein phosphorus does not have any lone pair. It does not have any lone pair. PCl4 positive, right? PCl4 positive. It's again tetrahedral geometry, right? Regular geometry, no lone pair. PCl6 negative, right? It is the octahedral geometry, regular geometry, no lone pair. So it's 0, 0 and 0. Option B is the one which is correct among all, right? Simple. And till now, I used to show you how to calculate the lone pairs and everything. You can solve the same question by that concept as well. Moving on to one more. The number of molecules having pyramidal shape. The number of molecules having pyramidal shape. As I told you a few minutes back, wherever you see 3 sigma and 1 lone pair, it's going to be pyramidal. It's going to be pyramidal. 3 sigma, 1 lone pair on nitrogen, my dear people, because there are 5 valence electrons of nitrogen, out of which 3 it is using, 2 will be here. So this one is pyramidal. ClF3, ClF3, 3 sigma bonds, 2 lone pairs. It cannot be. SO3, 3 sigma bonds, 0 lone pair. It cannot be. 3 sigma bonds, 1 lone pair. It can be, right? XeO3, 3 sigma bonds, 1 lone pair. Absolutely. BCl3, 3 sigma bonds, 0 lone pair. ClO3 negative, right? 3 sigma bonds, 1 lone pair. Absolutely. 3 sigma bonds, 1 lone pair. Absolutely. So how many? 1, 2, 3, 4, 5, right? So there are 5 species which have got basically the pyramidal geometry among all, right? Yes? You can check them up. These are the structures given, right? Do remember these structures as well. Among the following molecule expected to be stabilized by the anion formation. So see, when C2 gets converted into C2 negative, does it get stabilized or not? See, if the bond order of C2, right, increases on adding an electron, then we say C2 is getting stabilized after the addition of electron. C2 is the 12 electron species. As I've told you a few minutes back, 14 electron species will have the bond order of 3. 13 electron species will have the bond order of 2.5. 12 electron species will have the bond order of 2, right? So C2 has got the bond order of 2. C2 negative, 13 electron species has got the bond order of 2.5. So on adding an extra electron to C2, is its bond order increasing or decreasing? It is increasing, my dear people. And whenever after the addition of electron, bond order increases, you can say the molecule gets stabilized after the addition of an electron. The molecule gets stabilized after anion formation. So C2 is the molecule which is getting stabilized after the anion formation. Simple, because its bond order is increasing from 2 to 2.5. You can check the rest as well, right? Let's move on to one more, my dear people. Which of the following molecules does not contain the unpaired electron? Is there 14 electron species anywhere? See guys, have a look. If you talk about oxygen, it's a very common question. How many unpaired electrons are there in oxygen? If you write its molecular orbital configuration, it will be having 2 unpaired electrons, right? But it's di-negative. So both the unpaired electrons have got paired. So there'll be no unpaired electron in case of O2 di-negative, right? There'll be no unpaired electron in case of O2 di-negative. If you look at this molecular orbital configuration, O2 di-negative, it has got some 18 electrons, my dear people. So fill all these 18 electrons in these molecular orbitals. You won't see a single electron, right, unpaired in any of the molecular orbitals. And wherever in the molecular orbital configuration you do not see any unpaired electron, that is absolutely going to be diamagnetic. Well, if you write the others, if you write the configuration for others, absolutely they will be having the unpaired electrons, so they will be paramagnetic in nature, right? The number of species below that have 2 lone pairs of electrons. That have 2 lone pairs of electrons on the central atom. See guys, SF4 is a very common species. Sulfur has got 1 lone pair. 4 sigma bonds, 1 lone pair. It's seesaw, right? There is no lone pair on boron, right? Because it's already forming 4 sigma bonds. It cannot exceed its covalency beyond 4 anyways. Leave that. See guys, boron, it has got 3 valence electrons. And there is a negative charge, 3 plus 1, 4. And all the 4 valence electrons are used to form 4 sigma bonds. So no lone pair, right? 7 valence electrons, 3 are being used. So 4 electrons will be left as such in the form of 2 lone pairs. There are 2 lone pairs on chlorine. ASF3, arsenic is the nitrogen family element, right? It has got 5 valence electrons. 3 it's using. 2 will be as such in the form of a lone pair. PCl5, no lone pair. BRF5, there'll be 1 lone pair on bromine. XCF4, 2 lone pairs on xenon, right? No lone pair on sulfur. The number of species below having 2 lone pair of electrons on the central atom. This one species having 2 lone pairs, and this one more species having 2 lone pairs. So there are only 2 species wherein there are only 2 lone pairs of electrons on the central atom, right? Right, people? Well, these are the structures. You can check the structures as well at the end, right? Let me move on to one more, my dear people. Consider the given species CN positive, CN negative, NO, CN. Which of the following will have the highest bond order? See, if you talk about first of all, CN negative. CN negative, how many electrons are there? 7 plus 6, 13 plus 1, 14. It's a 14 electron species. It has got the bond order of 3, right? It has got the bond order of 3. CN positive, right? CN positive. Or let me talk about NO. Let me talk about NO. 8 electrons, 7 electrons, right? 8, 7, 15 electron species. 15 electron species has got the bond order of 2.5, right? So NO is done. CN. If you talk about CN, 7 plus 6, 13. 13 electron species has got the bond order of 2.5. CN positive, 12 electron species. 12 electron species has got the bond order of 2. Few minutes back only I have given the order. So wherever, my dear people, I mean, it's basically in CN negative, right? The bond order is maximum, that's 3. Alright, this is going to be our last question of the tonight's session, my dear people. And this is something which I'm giving you as the homework. Please and please do let me know the answer of this particular question in the comment section of this particular video, right? So at the end, I'm sure this session would have definitely helped you a lot, right? Or there is one more question, my dear people. This is something which you can do on your own. I'm sure about that. Number of lone pairs in case of XCOF4. Let me make its rough structure. There is double bond O. There are 4 fluorine atoms. 1, 2, 3 and 4, right? This is the rough structure of it. Xenon being the central atom has got some 8 valence electrons. Out of 8, it is using 1, 2, 3, 4, 5, 6. It's using 6. So there are 2 electrons left as such on xenon in the form of a lone pair, right? So there is 1 lone pair. How many sigma bonds? Asha, we are supposed to calculate the lone pairs only, right? So there is 1 lone pair. Perfect, people. So at the end of the session, my dear people, if you have not enrolled into the JEE 2022 crash course batch yet, do get enrolled as soon as possible, my dear people, right? Because this crash course is definitely worth it, right? And you are getting this crash course completely in affordable price in 1800. Your whole syllabus of physics, chemistry, mathematics is being done in just these 2 months, right? Apart from that, test series is included here. Study material is included, assignments are included. So whatever things are needed right now for your preparation, every single thing is included in this particular batch, in which you are getting trained by the best teachers of Vedantu, my dear people, right? So you can take the English batch or the English batch, depending on your convenience, right? In this particular crash course one, and get enrolled as soon as possible, I'm telling you, right? Because I don't want you to miss more sessions in this particular batch, right? And how do we get enrolled into this particular crash course batch, my dear people? This is the video which you guys are currently watching. I would want you guys to drag the video a little down, click on show more, and after clicking on show more, you will be getting a lot of links over here. JEE Main Target 2022 crash course, right? Click on this particular link. After clicking on link, click on buy course, and you are just getting this course only for 1800, my dear people, which includes every single thing, be it course completion, be it syllabus completion, whatever things are needed right now for you guys for your preparation. All those things are incorporated in this particular batch. It's my personal suggestion, do get enrolled in this one as soon as possible. And if you have not liked the video yet, please do like the video, share the video with your friends, and do subscribe to the channel as well, right? It was nice meeting you. I'll see you guys again tonight at 9:30, wherein we are going to have the one short session from the chapter electrochemistry on this particular channel itself, right? So do join me again at 9:30 on this particular channel with the chapter electrochemistry, my dear people. Till then, you take care. Bye-bye. God bless you all.